So, hello everyone. We're going to be continuing our finance unit here today with compound interest. So, compound interest is probably going to be the most interesting form of investment scenario for you because it is the type of interest scenario where you're going to be saving money for your own retirement in the future. We're actually going to be doing a more basic version of that today. Those types of investments are a little bit more complicated because they require you to put investments in like regularly, like every month, up until the time you retire. This is more of an investment where you're putting the money in the bank, leaving it there for a certain amount of time, walking away so you don't put any extra money in, you don't take any money out until the very, very end of the investment. So the types of investment I'm talking about do actually exist. GICs, or guaranteed investment certificates. Savings bonds is another one. And the banks will often give you higher interest for those types of investments because you are signing a document saying you're going to leave the money in there and you're not going to take it out. Now, you probably can take it out at a high penalty, tax penalty. But if you leave it in there for the amount of time, because they are using your money to invest, remember, from their previous lesson, they give you a higher interest rate for that. So interest in compound interest is gained not only on the initial investment, but also on the interest that you're making previously. And that's what makes compound interest different from simple interest. These follow a geometric sequence. You've already studied this in the sequences and series unit, and that's the type of pattern that they're going to be following. So that comes back a little bit in this unit as well. So let's take a look at our first example here. And I believe I got this information off of the internet a few years ago. I don't know if these numbers have changed, but I wanted to use a real world scenario. So the Royal Bank offers a 10-year GIC interest rate of 3.5% per annum, compounded annually for initial investments of $1,000 to $99,999.99. You want to invest $1,000 in this GIC. How much money will you have in the bank after 1 year, 2 years, and 10 years? So as always, when we're looking at a pattern in math, it's always a good idea to start with a table of values. Now this table is a little bit complicated, so I'll try to explain it here. We've got our current year, how much time has elapsed in years between each successive payment of interest, the start of year amount, how we calculate the interest, and you're going to notice that this is actually the simple interest formula here. So the simple interest formula is used in the compound interest scenario. And then the amount we have at the end of the year. So what we're doing here is we're pretending that we're investing money on the last day of December of a year, and then that money is going to stay in the bank for the whole first month of January of the next year, but it'll only get interest at the end of January. So that $1,000 right here is our first payment that we make at the very end of December. All right. So now we're going to get into the first year that $1,000 is in the bank. So the length of time that it's going to be in the bank for is 1 year. At the beginning of the year, we're going to have $1,000, right? In January, we have $1,000. What do we have as interest at the end of the year? Well, we're going to use our PRT formula from our simple interest equation. So 1,000 is our principal. 0.035, and just a reminder of where that came from, it is a 3.5% per annum investment. So 0.035 is just this number divided by 100. Times 1. Now, why is it multiplied by 1? Because now we have to get into explaining a little bit what the word compounded means. So see how it says compounded annually here? The word, exactly, chat. The word means how many times per year are you getting paid interest? Now that compounding frequency can change. We're going to actually see examples later on where that could be compounded monthly. Now, if it's compounded monthly, and I talked about this in the previous lesson, and I had somebody make a mistake on this, and this is probably one of the most important things, a little bit of foreshadowing for what's coming on in the later part of the lesson. If you're getting 3.5% per year and you're compounding that monthly, that doesn't mean you're getting 3.5% every month. If you're getting 3.5% interest every month, you need to tell me what bank you're banking at. But what we're going to see is if you're compounding monthly, what the bank does is they take that 3.5% and divide it by 12 and give you 12 equal interest payments of that much smaller interest amount, so that over the course of the year, they add up to 3.5%. All right? But because we're compounding annually, we don't have to worry about that because we're getting 3.5% at the end of the year, and that's when we get paid the interest. So that's where all of these numbers come from, the PRT and the T being 1 year because we're compounding annually. If I add the $1,000 that I had at the end of the previous year to the $35 that I have at the end of the first month of the year that we're actually calculating our interest in, we've got $1,035. Now and here is the big difference between compound interest and simple interest. When we did our last lesson, our next value to calculate our interest would have been $1,000 again, but that's not what happens with compound interest. With compound interest, at the end of that first year, when we I think I said month, sorry. At the end of the first year, when we have $1,035 in the bank, we're going to use that $1,035 as our starting amount for the next year. And look at what happens right here. That's what makes this a compound interest scenario instead of a simple interest scenario. We're not using the $1,000 anymore. We're using $1,035 as our new principal for the next year. And that means our interest amount is going to be slightly higher. So I'm just going to do this off camera here. I got to pull up my calculator. If you have a calculator, you can do it too. Make sure I don't make any mistakes. So 1,035 times 0.035 times 1 gives me 3623 approximately. It's 36.225. I'm going to round it off to 3623. All right. And then I add that amount to the amount I had from the previous year. So this is the interest gained during the second year that money is in the bank. And I'm adding it to the previous amount, which is, I believe, $1,071.23. Now, if this was a simple interest scenario, I would have just added 35 and I'd be at 1,070. So I know $1.23 doesn't seem like that much more, but that's just going to compound, no pun intended, as the interest compounds, okay? So we have to fill out the rest of this table. However, I wanted to show you how we could do this with a spreadsheet instead. Spreadsheets are glorious when it comes to doing calculations that repeat themselves over and over again. I'm hoping you can see this clearly enough. I'm going to be typing in some calculations. They'll be a little bit smaller, but again, hopefully you can kind of see them. So what do we have at the end of the year? We have 1,000 plus 35. I want to enter that as an equation, okay? So I'm going to write equals in this cell. You always have to start an equation with an equal sign in a spreadsheet. And I want it to equal this quantity plus this quantity. I don't want to just import it in because I want it to equal that amount. Now I want you to notice what happened over here. It immediately matched what I put in there. And the reason it did that is because I said look at what the equation is of this cell. It's equal to K3. K3 is this entry. I want all of these start of year amounts to equal the previous end of year amount. All right? How do we calculate our interest? Well, I'm going to put a formula there too. I'm going to put equals. Our interest is our start of year amount times, now the button on the keyboard for times is the asterisk above 8. Okay, and that's 0.035, which doesn't change. So I'm just going to type that number in. Times 1, which also doesn't change. and I get my 3623 that I had on my on the smartboard note. Okay. How do I then get this amount? Well, watch what I can do. If I click on this, which says K2 plus J3, right? These two numbers here. If I drag that down, it's going to change it to be K3 plus J4, which are the next two diagonal cells to add together. And I'm actually going to delete this cell because I want to now select these three cells and drag them down, and I can now keep going on and on and on. So if I now select all of these and drag down, I can go as far as I want, and it's going to calculate how much money I have at the end of the year based on all of the new interest. Now look at all the interest amounts, how they're changing. They're getting bigger and bigger and bigger. And they're not getting bigger linearly. The change from 35 to 36.23 is $1.23. That is not the same amount from the change from 36.23 to 37.49. So the amount of interest keeps compounding. That's what compounding means. You're getting interest on your interest, which means you keep getting more and more interest as the years go by. Now, one thing we can do here is we can do, and I'm going to cut this table off at 10 because it actually just said to go to 10 in our note. And I can share this spreadsheet with you afterwards. Let's do our first differences. Now let me just format this cell same as that one. Oh, no, that's not what I wanted to do. Let me undo that. I want to format all of these cells the same as that one. Okay. So the reason I did that is because there's actually a button right here that says format as currency. That means you can take any value, and if you click on that, it'll change it into dollars for you, so you don't have to do it yourself manually. And I had already done that with these cells, so I hadn't done it with these. Let's do our first differences. So if I wanted to calculate our first differences, I would take this number and subtract that number. And I want to do that all the way up. So we're going to do that all the way up. I'm not going to go to here because it would ask to subtract 1,000 by these words, and that wouldn't work, right? There's always one less subtraction. This is not a constant value. So our first differences aren't constant. All right? That means this is not a linear relationship. So let's do our first ratios. We had learned to do this with exponentials, right? So I'm going to take this cell, and I'm going to do this number divided by this number. Let me make that a little bit bigger. Too big. Too small. Of course, it would be the one in the middle. And I'm just going to drag that up all the way to here. Now, this one here is a little bit off simply because of how this was rounded. Remember that this was 36.225, and it rounded off, I think it was 225. It rounded it off downwards, okay? But technically, it is pretty close to 1.035. That is a common first ratio. And if we have a common first ratio, chat, what kind of function is compound interest? That is correct. It is an exponential. Okay. So let me go back to the smartboard here. I'm not going to fill in the rest of these values. The table of values on the spreadsheet will do that nicely for us. Let's just move over to the next slide. Now it says, had this been a simple interest problem, would you have made as much money at this point? And I'm sure you already know the answer to this, but let's just actually calculate it. If I did my simple interest formulas of I is equal to PRT, now I'm going to do it for the full 4 years. So at the end of the 4 years, I'm just going to check what we had on our spreadsheet here. I don't think I closed that window. After 4 years, we had 1,147.52. Okay, that was with compound interest. For simple interest, let's do the calculation. We have $1,000. Our interest rate is 0.035, and our time is 4. Now we can do this calculation in our head because 1,000 times 0.035 is just 35. And 35 times 4 is the same thing as 70 times 2, which is just 140. So our total amount for simple interest would be the addition of 1,000 plus 140, which would be 1,140. Now compare those two values. It might not seem like much, $7.52. But that's after 4 years. If that interest keeps accumulating because of the compounding nature of it, it might be significantly more in 30 years, right? So the idea here is that simple interest is the best thing to have when you're borrowing money, but compound interest is the best thing to use when you're investing money. Unfortunately, there may be scenarios where you will compound interest when you're borrowing money, specifically a credit card. If you don't pay the credit card off at the end of the month, you may be compounding your interest there to pay. But generally speaking, like I explained in the previous lesson, if you borrow money to buy a car, for instance, that is going to be calculated as a simple interest scenario because it is not fair to get charged interest on interest when you have to just take a loan out to buy something. Okay, but you definitely want it to compound when you're investing. So even though the pattern isn't as clear as for a simple interest problem, the pattern still exists, and that is the first ratios that I showed you. And I'm actually going to show you exactly how this formula was developed in a couple of minutes. But this is the formula here for a compound interest question. And I really firmly believe that everybody should be memorizing that formula. It is the basic idea of how you're going to invest money for your own retirement. Anybody in chat know how much money they suggest you save up through either your pension or your own investments for your own retirement? Yeah, that number came up earlier in the previous lesson, 800,000. It's actually 1 million at this point, I believe, because of inflation. So the minimum amount of money that is recommended that you save up by retirement age, which is, depending on what kind of money you're going to be making, that could either be 55 or 65, $1 million by the time you're that age. So take your age now, subtract 65 by that age, and that's how many years you have to accumulate $1 million. Now, this is not the formula that you're going to use to do that. It's the basic version of that formula, because this is a formula that if you use it, you're putting in a certain amount of money in the bank and you're walking away. You don't put extra money in. The actual form of investment that you're going to use to make money for your retirement is usually an annuity. In an annuity, you're putting regular payments in every month for 20 years or 30 years or 40 years, whatever it may be. But that's a much more complicated equation, so I didn't want to start with that one. We're starting with this one. But you need to understand this one to be able to understand that one. And I believe it's actually one of the least understood equations by people, because when I walk around in society and tell people I'm a math teacher, one of the most common things that I've heard in my life is I hated math and I wish they would have taught me finance. Well, you won't be able to complain that way, folks. Not that I thought you would have anyway, but you're going to know a little bit of finance by the time I'm done. So these are the variables in the equation. You'll notice that A and P are the exact same as they were in the simple interest formula. There is a difference with I and N. Now, the first thing I want you to notice here is that I is not a capital I. Lowercase I, is interest rate per compounding period. And I'm going to explain that. I started to explain it a little bit earlier. I'm going to explain it a little bit more later on as well. N is the number of compounding periods. So how many times are you getting paid interest over the life of the investment? So let's move on to the next slide here. Now, I'm actually not going to fill this table in here, folks. I had left it here in case we were going to do everything by hand, but at the last minute I decided to use a spreadsheet. So I'm going to share that spreadsheet. I'll just write a spreadsheet was used here, and it was just to show you that the first ratios were 1.035 all the way down, and it was exponential, okay? Or geometric. All right, so this is a difficult slide for me to explain. I'm going to try to do my best. I want to actually prove to you how the formula A is equal to P times 1 plus I to the n, is created, okay? And it's based off of a recursion. If you did and I'm assuming most of you have done the sequences in series unit, you did do some stuff about recursion and the iterative process. So here's how this works. And now I wrote it off to the left here so I can write a little bit of stuff on the right. So A0, we start off with A0 is equal to our principal. So our starting amount was $1,000 on the previous example. To calculate the interest, we took that $1,000 and we added PRT to it, right? Or in this case, A0 RT, which would have just been the $1,000 times the interest rate times the 1. So that's what this is. Now, if I replace A0, didn't want to change the color for that. If we replace A0 by P, we get our P plus PRT, which is actually our simple interest formula. But notice the recursion. To calculate A1, I needed to substitute A0. That's what recursion is, right? Using a previous equation to calculate a new value for that sequence. Well, what about A2? Doesn't A2 require A1? Wouldn't we end up with A1 times 1 plus RT? But A1 was equal to P times 1 plus RT. Wouldn't that mean that A2 becomes A1, so P times 1 plus RT, times 1 plus RT? And if we did A3, wouldn't it be P times 1 plus RT times 1 plus RT times 1 plus RT? We just continuously keep multiplying by 1 plus RT. And when we do that in math, that becomes an exponent. And that's what makes this an exponential. It's the fact that we have to recursively use previous values into the newer values, and it just continuously multiplies that 1 plus RT over and over and over again. Now, R times T is going to be called I. And that's where we get this formula. So that's the proof using recursion, which is a sequences in series idea, to start with the simple interest formula and end up with the compound interest formula. Okay, let's talk about varying compounding frequencies now. How does changing the compounding period affect your amount of money that you would get, your return? In order to introduce this properly, I have to first introduce you to some terminology. And you're going to have to know this. Annually means every year. Pretty simple. Semi-annually means twice a year. Now, I want you to think about this in the terms of our interest. Okay? If you're getting 0.035 per annum. 3.5% per annum. But I'm splitting that up to 2 payments per year. Wouldn't it make sense that you would have to divide that by 2? Now, I'm going to introduce you to one of my weaknesses. I don't know why my brain does this, and I'm hoping by talking about my weakness, I don't infect you with it. But for some reason, when I see the word quarterly, I think of the number 3, and it sometimes messes me up. Why am I thinking number 3 when I say quarterly when I'm talking about a year? Analyze my brain. If you divide a year into 4 chunks, how many months elapse? Yeah, exactly. That's, for some reason, I think 3 times a year, and then I think the number I have to use is 3. And I've seen students make the mistake too. And I hope it's not because I say the mistake that infects your brains with that mistake. But please be careful. Quarterly obviously means 4. The word quarter is right in there. All right. But it does mean every 3 months. So we would take that 0.035 and divide it by 4, because we have to add up all those little chunks to give me 0.035 at the end of the year. Bi-monthly, 6 times per year, twice per month. And I'm always shocked at how many students sometimes don't remember some of these numbers. Monthly is usually remembered, but I have had some students not know that there's 12 months in a year. This one is the one that messes people up the most. If anybody has a job, you usually get paid bi-weekly, which means every 2 weeks. If you get paid every 2 weeks, how many times per year are you getting paid? So chat just gave me the correct answer of 26, but you would be amazed at how many people tell me it's 24. And the mistake that's made there is that people think that every month has 4 weeks in it. So they just divide a month by 2 and then say times 12. But there's 52 weeks in a year. If I need to know how many 2-week periods there are, I'm going to divide that by 2, and that gives me 26 times per year. Okay? So that means that when you get a job, if you're getting paid bi-weekly, there are 2 months out of the year where you actually get 3 salary payments. And then weekly, I already answered that one. Daily, how many days per year? Chat. It's a race. Technically 364.25, but I'll accept 365. Yeah, we're going to use 365. And we need to know that because if a question says that something is compounded quarterly, you have to do something special to the interest. And we're going to see that in the next example. So 2 people invest in the same mutual fund. The fund offers 10% per annum on investments of $20,000 or higher. We're going to assume that these 2 people invest the full $20,000. Sarah chooses to invest in this fund for 5 years, but selects the option to compound the interest semi-annually. Steve chooses the same fund and also invests for 5 years, but chooses to compound annually. Will the final amounts be the same? Now, why are we asking will the final amounts be the same? I want you to understand that both people are getting 10% per year. Both people are getting 10% per year. The only difference is Sarah is getting 5% at the half-year mark and another 5% at the end of the year. Will both amounts be the same? So this is the way you're going to set up these questions. The most important thing when solving compound interest questions, in my opinion, is calculating the I and the N first. And if you can get these 2 quantities down, you won't have any problems with the rest of the unit. These are the 2 quantities that mess people up the most. So let's take a look at Sarah. So Sarah, and I'm going to write down all of the quantities here. For some reason, I keep losing my pointer, so I'm having trouble seeing where my pen is on the screen. Oh, it came back. Okay. So let's list all of the things we know. So the amount of money that Sarah is going to be investing is $20,000. That's our principal. What is the I? The I is 10%, but we have to divide that. It's per compounding frequency. The word per means division. We're dividing that by 2 because it's semi-annually. Had it been quarterly, we'd divide by 4. If it was daily, we'd divide by 365. It's semi-annually, we're dividing by 2. And that's 5%, which is 0.05. Our N value, and this is the first time we're calculating the number of compounding periods. Our N value has to be based on how many years are going by, as well as how many payments per year you're getting. We're investing for how many years again? Okay, I'm going to have to use my mouse. My pen is not working properly. We're investing for, 5 years. Okay? So we're investing for 5 years. We're getting paid twice per year. So if we're investing for 5 years, twice per year, we're going to multiply 5 times 2. And this is the reason that students mess this up all the time. One of them is a division. Most of the time, there are exceptions to that rule. And one of them is a multiplication. And you have to remember which one's which. But if you understand, what does I mean? I is the number of interest payments you're getting. I is the chunks of interest you're getting every time you get paid interest. And that's based on your compounding frequency. If you're breaking up your year into 4 quarterly payments, you're breaking up your interest into 4 smaller interest payments. So you're dividing by 4. Here we're doing semi-annually, so we're dividing by 2. So I'm sorry I'm repeating myself over and over again, folks, but source of a lot of frustration for me is students multiplying I by 2 and dividing N by 2 because they don't remember how they work. So if you can get past that, you won't have any problems at all. So let's put everything into our formula now. So this is Sarah's amount. $20,000 is our P. 1 plus 0.05 to the power of N, which is 10. And I'm going to need my calculator for this. So I'll just quickly do it off to the side. So 20,000 times bracket 1 plus 0.05 bracket to the power of 10 gives 32,577.89. Not too shabby for a 10-year period, right? You're starting with 20,000, you've made $12,577.89. So if you just look at the difference between those two, that's the amount of interest you've gained. Let's look at Steve. So Steve's principal is still $20,000, same thing as Sarah. Steve's interest is calculated annually. That's just divided by 1. So that's just 0.10. Steve is investing for 5 years as well, but it's times 1 payment per year. Most students, when it's annually, won't even do this calculation, but I just want to show you what's going on. And I want to write Steve's formula a little bit higher up so we can compare it to Sarah's formula, okay? So for Steve's final amount, we're going to do 20,000, 1 plus 0.10 to the power of 5. Now look at the difference. The interest rate is higher for Steve, but the power is higher for Sarah. Both of them are getting 10% per year. Let's calculate Steve's final amount. So again, I'll do this off to the side here. 20,000 times bracket 1 plus 0.10 to to the power of 5. And that gives $32,210.20. Steve made less than Sarah. Why? Both of them are getting 10% at the end of the year. What's happening with Sarah's interest that she ends up with much? I mean, that's what, $360 more? That's not a small amount of money. And the reason is because of the magic of compounding interest. Sarah got interest at the halfway mark, and that interest gained interest by the end of the year. And that's what's making the difference. The magic of compound interest. So, to summarize this, folks, the most important thing is, do you understand how to calculate I and what it is? If you can understand what it is, same thing with N, then it's just plugging everything into the formula. Now, to give you a little bit of foreshadowing as where we are going with this, what if I gave you a scenario where you knew all of these values, but you didn't know I? Would you be able to isolate I? This one would not require a logarithm. What would be the first step here? What would be the first step? Yes, you're right. We are going to use roots. The first step would be to divide 5,000 by 4,000, right? So we'd end up with something like, I think it was that 1.2. Sorry. What's 5,000 divided by 4? 1,000. I think it's 1.2. Anyway, whatever. 1.25? Okay. Whatever. It doesn't matter. If I had told you that that was equal to x squared, 1.2. Okay, it doesn't matter. If I told you that x squared was equal to 5, let's just forget about the 4,000 and 5,000. How would you isolate the x? You would square root, right? Well, here, the I is trapped inside of a power of 10. What destroys a power of 10? It would be a 10th root. But we wrote 10th roots as fractional exponents when we learnt our radicals unit. So you're going to end up needing a fractional exponent here. Now, where you will need logs is, what if I gave you, as a second example, same scenario, but this time I tell you that the interest rate is 5% and we don't know the exponent. That's where we would need logs to solve. I mean, you could also do trial and error, but who wants to do that? Right? So, isolating all of the other variables. I didn't show you how to isolate P, which is actually tomorrow's lesson. That's extremely easy. But isolating I and isolating N are a little bit more complicated, but you have all the skills necessary to do that now. And that's where we're heading with this next. So I'm going to stop recording there.